Alright, I've continued reading Chapter 2 of Fire in California's Ecosystems. Main concepts we're going to be talking about there today is the moderating effect that the ocean has on our coastal cities. And then we're also going to dive a bit deeper into the rain shadow effect, which is one of the most important concepts to know for fire in California, because that determines where you're going to be picking up the largest amount of rainfall, and then that determines the vegetation that you have in an area. Before we get into that, though, I want to talk about a fact that I read in this book maybe a few days ago that I've been thinking about just because it didn't really make sense to me how this could even be true, but I think I finally figured it out. So the fact is that 4.4 million acres to 13 million acres used to burn every single year in California. This is when Native Americans were using fire to their advantage. They're using it to manage vegetation, to promote certain crops, to protect their villages, in warfare, hunting game, to promote certain materials. Fire was the number one tool that they had to manage the landscape. So there was a lot more fire every year in terms of acres burned. There was also natural ignitions like lightning up in the Sierra. And that would also be part of that 4.4 million acres to 13 million acres that would burn. Now, the reason that number was so unbelievable to me was the worst wildfire year in recent memory is 2020. You probably can think back to, I believe it was September 9th, 2020, where it looked like there was a full-on apocalypse in California. The sky was that kind of eerie, dark orange color, and it remained like that for quite some time. The satellite imagery showed the entire state just covered in smoke. And in 2020, we burned 4.3 million acres. So less acres burned in the worst wildfire year that we have in recent memory than what they were routinely burning every single year. And in some cases, the Native Americans, they might have had 3 times as many acres burned as what we had in 2020 every single year. So I was thinking about, how could that be possible? Like, was the air just constantly ridiculously smoky from summer through fall? And was that just incredibly unhealthy? And then as I was actually driving home the day I reported that fact, it kind of clicked to me what's going on here. It's possible to have more acres burned, but have less wildfire smoke and have your fires be a lot less bad, if you want to put it that way, a lot less extreme. So that might be counterintuitive. You have more acres burned but less smoke. How does that make sense? Best way I could put this is, if you have routine fire every single year, like the Native Americans did, then the fuels wouldn't accumulate. You would have your ground fuels, maybe some grasses, and then you'd have your big trees, but you wouldn't have the ladder fuels where it's grass, brush, tree. That's exactly the situation that we had in 2020, where because of a history of fire suppression, all of the fuels have been accumulating. So you have what's called ladder fuels. It goes grass, brush, tree. So then if your grass catches on fire, your brush catches on fire, your trees catch on fire, everything catches on fire. That's why we had so much smoke produced in 2020, because we had hundreds of fires start because of all the lightning from Tropical Storm Fausto. But those didn't just stay on the ground. It turned into crown fires, so then everything was just burning. So even though 4.3 million acres burned, you had a lot more within those 4.3 acres burning. The comparison is back in the Native American days. They would start the fires on the ground, but those fires would stay on the ground. And it'd burn out some grass, but it wouldn't have the ladder fuels to be able to jump into the trees. So you could have a situation where you burn 13 million acres per year, but maybe very little of that is your old growth forest burning. It's just some grass, which would be producing a lot less smoke than if it's grass, brush, and trees all burning at the same time. So the basic summary there is, it's this weird idea that more fire is actually good because it leads to more frequent, less intense fire with less danger, less smoke, less impacts, less threat to property and life than when you have less frequent fires that build up the fuels and then become way more extreme. Just thought that was an interesting idea. I certainly want to learn more about that as I go forward in this process. I'm sure it covers it more in this textbook because that fact was kind of in the introductory chapter. So now I'm on to chapter 2. It's California fire climate. And the two main things I was learning about today, marine influence and the rain shadow effect. So marine influence, we can go through that pretty quickly. It's the fact that the coast is moderated by the ocean. And what I mean by that is during winter, one of the warmest places in California, so during the cool months, is going to be your coast because the coast will be mild while inland areas are cold. And then during summer, so your hot months, the coast is going to be one of the coolest places. So while your inland areas are hot, the coast is still just mild. Now the reason for this is because land heats up and cools down faster and more than the ocean. That has to do with specific heat capacity, which is a very kind of sciencey term. Not going to go into the full definition of that. The best way to understand it though is if you took a glass of water and you took a piece of metal and you put them outside for 3 hours in the peak of the afternoon sun, and then you came back 3 hours later and you put your finger in the water, might be warm, but yeah, it might just be some warm water. Probably isn't going to be that great for drinking. But if you put your finger on the metal, you might burn your finger. And that's because the metal heats up a lot faster than the water does. And then in the same situation, on a very small scale, the air right above that metal would be a lot hotter than the air right above that water because the heat transfers between your material and the air above it. Same thing is happening on the scale of California. In the Sacramento Valley, we're heating up a lot more during the summer, and we're cooling down a lot more during the winter. And then on the ocean, there's not as much change. So just throwing out some numbers, maybe in Sacramento, your average temperature in summer is 80, and then during winter, it's 45. Talking about night and day. And then on the ocean, you go from maybe 48 degrees to 56 degrees. Much less of a change. Same is true for the air above the land and the air above the water. Now, in California, we usually have northwesterly winds. So that's going to push some of that air that's above the water over our coastal cities. And that's kind of the punchline right there. So because the coastal cities are near that ocean air gets pushed over them. And then during summer, that's like natural air conditioning. And then during winter, it's kind of like some natural heating. But overall, it just has a moderating effect on your temperatures on the coast versus inland areas where there's a lot more variability. So hopefully that made sense. Now let's get into the final topic for today, which is the rain shadow effect. Brief summary here. Rain shadow effect, it's if you have a mountain like this, your winds are going to come in, let's say this was with a storm, and your wind can't just go through the mountain, so it's going to be lifted up. As your wind and your air is lifted up, the windward side of the mountain, it's going to cool down. Cold air can't hold as much moisture as warm air can, so some of that water vapor is going to be squeezed out and form clouds, and then you're going to squeeze it even more, and you're going to get rainfall. Just like, when I say squeeze, I mean it's almost like squeezing a sponge. Your air rises up, cools down, squeeze out the sponge, you get a lot of rainfall on the windward side. And then that air keeps traveling, and as it goes over the mountain range, now on this back end it's descending, it's going to be heating up, but a lot of the moisture has already been squeezed out of it, so there's less moisture left over, so you don't get as much rain on the leeward side of the mountain. That's why you'll often have dense forest on the windward side and then deserts on the eastern side of large mountains. Now there's two important concepts I'll go over today about that determine how strong the rain shadow effect is going to be. I kind of paused there for a second because I can sort of think of four, but I'm only going to be going into two. The two that I'm not going to go into is obviously how tall your mountains are. That's going to be a factor. The taller the mountain, the more lifting you're going to have. And then also where you are in proximity to the storm is also going to matter. If you're way up in Northern California, where the storm is first moving in, you're going to have a lot more of the moisture than if you're all the way down in Southern California. By the storm gets to you, a lot of that moisture has already been squeezed out, so you'd have less rainfall. Not going to get too far into those because I think both of those are pretty self-explanatory. The two concepts that I'm going to get into that determine the strength of the rain shadow effect are the steepness of the slope and then the direction the slope is facing. So for the steepness of the slope, if you have a gradual slope, that lifting motion is going to be spread out over a much larger area. So then your rain is going to be spread out over a much larger area. So let's say you have, just using simple numbers, 10 inches of rain with this storm that's coming in. If you are spreading it out over 10 miles, then you're going to get 1 inch per rain or per mile. If you have a slope that's almost just straight up, it's maybe your width is 1 mile, all of that lifts up in one place, you get 10 inches of rain within 1 mile. And, well, those are made up examples, so I'll drive this home with an actual example. So in the Northern Sierra, we have a pretty gradual slope, and we have about 24 inches of rain there every single year. Then around the peak near Lake Tahoe, which is going to be a lot steeper, we have about 60 to 80 inches of rain per year. And then to complete the kind of rain shadow effect on this, on the back end of the mountainsides from Lake Tahoe, I believe it's called the Modoc Plateau, that's where you have 8 to 24 inches of rain. So gradual slope, 24, steep slope, 60 to 80, back end, where a lot of the moisture has already been squeezed out, 8 to 24. Perfect example of the rain shadow effect. And how steepness of slope impacts how much rain you get per year. Now, the other one is the direction the slope is facing. So, when a storm is coming in, a lot of surfers know this. You're going to have southerly and southwesterly winds, and then after the storm comes through, your wind's going to shift back to the northwest. The reason for that, you could think about the trough that a weatherman shows on TV. It's almost shaped like a U. I'll go like this. As that storm is coming into California, the area where the storm is on this trough is going to be on this side right here. So as it's coming in, your winds are blowing from the southwest. And what I meant by surfers is, the reason surfers know that is because you'll go to beaches that favor south and southwest facing wind. Or south-southwest winds, where those kind of winds make the surf good. That's why I just kind of intuitively knew that this was a thing where south winds before the storm, northwesterly winds after the storm, but I never really thought about what was going on till the textbook explained this trough process. So storms coming in, you have southwesterly winds, and then as the trough continues to move through, so after the storm, now your winds are coming from the northwest. So your winds go around the trough like that. So southwesterly to coming from the northwest. So how that relates to the rain shadow effect is as your storm's coming in, your winds are going to be coming from the south and from the southwest. So the mountain ranges that are going to pick up the most rainfall and have the largest rain shadow effect are going to be the mountain ranges that face south and face southwest, because that's where your mountain is going to be at a right angle to your winds, and that's where the lifting motion is going to be strongest. An example of that is the Santa Cruz Mountains, which are south-southwest facing, and those pick up 40 to 60 inches of rain per year, versus the peninsular ranges, or the peninsular range, which is parallel to your wind storm direction, and then that's going to have about 16 to 24 inches of rain per year. So just to sum all that up, if you have a steep slope that is at a right angle to your wind direction, you're going to pick up a lot more rainfall than a gradual slope that's parallel to your wind direction. And then the situation where you pick up the smallest amount of rainfall is going to be on the back end of the mountainside where all the moisture's already been squeezed out. Example of that would be something like Death Valley, which I believe gets 2 inches of rain per year. So, talked a lot about different wildfire concepts throughout the course of this video. Hopefully you learned something. If you want to learn more about wildfire, I'm gonna slowly work my way through this massive textbook right here, and I'm on page about 13 or 14 out of, I don't know, 500 or something. So I've got a long ways to go. If you want to join this journey, you can just stay updated, and thanks for watching.